In a previous tutorial, we looked at point groups and assigning point groups to different compounds based on the symmetry elements present within that compound. Today we'll be looking at character tables of those point groups, and we'll be looking at extracting the bonding orbitals for both sigma bonding and pi bonding from these tables. So in a table like this one here, where the point group is C2V, and an example of that would be water, H2O. We looked at that last time. And in this character table, you'll see the point group label on the top left corner, and you'll also see the symmetry operations that are available in this point group. Now in this case here for C2V, we have E, which is the compound by itself without having any symmetry operation performed on it. Then we have C2 available, and then following that we have a mirror plane on the XZ axis, and as well as another mirror plane on the YZ axis. Now the coefficient in front of these in this case is just 1, but in other cases we will see that there will be different numbers, and if we add these numbers, so if we are actually adding the operations, or the total number of operations that are available in this character table, we'll come up with the order of this point group. So in this case here, 1 plus 1 plus 1 plus 1 would give us an overall order of 4. And we'll take a look at other examples in which this is not the case and we actually have coefficients here. And on the left hand side here, we have the symmetry representation label. And A versus B is just symmetric versus antisymmetric with respect to the principal axis of rotation. In the rows that we have here, so this row, for example, right here, would be the representation for A2. And one specific square would be the character in this case. Alright, so we can actually walk through an example H2O, and we can see how we can come up with the orbitals that are used in the sigma bonding in H2O. Now on the side here you'll see those functions, and these are basically just the symmetry functions, and we'll be using them shortly. So if we have H2O in this case, and remember water is bent, we have 2 lone pairs on the oxygen, and let's assume in this case here that the z-axis is pointing up and the y-axis is to the right. So that means the x-axis would be pointing outside of the board. And let's redraw the character table that we had earlier. So we have the C2V character table, we have the symmetry element E, we have the symmetry element C2, sigma V, and this right here is the XZ axis, and we have sigma V that is along the YZ axis. And in this case here we're looking at sigma bonding. And now what we want to do is actually see how these bonds change with each of these symmetry operations. So if the bond actually moves, so if the hydrogen's atoms move, then we would assign that hydrogen a 0. And if it stays in the same location, we would assign it a +1. In this case here, we have 2 hydrogen atoms bonded to the oxygen. So if we keep it the same, both hydrogen atoms are in the same location, so this would be a 2. Now if we do a C2 rotation, so we have the oxygen, and let's take a look through the principal axis. So looking down on the water molecule, we would see the 2 hydrogen atoms pointing downwards, and this right here would be the C2 rotation axis. Now with the C2 rotation, both atoms move, and so in this case here, it would be assigned a 0. In the case of a sigma V, this is a mirror plane along the XZ plane. So remember, the x-axis is coming out of the board, and so we're looking at the mirror plane that is cutting through the water molecule, and we have both protons, one on the right and one on the left of the mirror plane. In this case here, both hydrogens exchange locations, and in this case we would assign this a 0. In the very last case here, so let's call this sigma V prime just to distinguish the two of them. So this is sigma V, and the very last one here would be sigma V prime. All of those 3 atoms are in the actual plane, so none of them move. And in this case here, both hydrogen atoms stay in the same location. Now what we find here is the reducible representation. Once we have the reducible representation, we can try and find the irreducible representation by following the following equation. So if we go back to the actual character table, you'll see we have 4 rows. So there's A1, A2, B1, and B2. So we want to find the number of representations for each one of those. So we'll start with A1. So in the case of A1, the equation is as follows. So you would take the number in the representation, in this case 2 here, and you multiply that by the coefficient, which is 1 for E, and you would multiply that by the character that is in that table. So in this case here it's +1. And you would do that for all of these representations. So in this case here, the next one is going to be 0 times 1 for the coefficient times +1 in the table. The next one is going to be 0 times 1 for the coefficient and +1 in the table. And lastly, the last sigma V, we have 2 as the representation times 1 for the coefficient and +1 in the table, the character. And we would divide all of this by the order, in which case here is 4. So here in this case we have 2 plus 0 plus 0 plus 2 over 4, so that's 4 over 4, and so we have 1 A1 in this case. In the case of A2, we would follow that same logic. So in this case here it would be 2 times the coefficient here, which is 1, times plus 1, and you'll see that in A2 it's plus 1, plus 1, minus 1, minus 1. So we don't have to refer back to this. So times 1 plus, the next one is going to be 0, and the following one is going to be 0. And the last one, in the case of sigma v prime, we have 2 for the representation times 1 for the coefficient times negative 1, right? And that's coming from here. And divide all of that by 4. So in this case here, we have 2 minus 2 over 4, so that's 0 over 4. So we do not have any representations for A2. Now, if we do the same for B1 and B2, we would realize that in the case of B1, we have 0 B1 representations, and in the case of B2, we actually have 1 B2 representation. So overall, the irreducible representation would be equal to 1A1 plus 1B2. Now, what does this mean to us? Now, we are looking at the sigma bonding, remember. In this case here, we can go back and see which orbitals are listed under A1. In this case here, we have the s orbital and the pz orbital. Now remember that this here is just a representation of the s orbital. And we also have the B2, which tells us that we have the py orbital and we have the dyz orbital. Now remember, we're looking at oxygen and we're looking at sigma bonding, so we would be using the py orbital in this case. So if we were to draw what we call SALCS, so SALCS are symmetry adapted linear combinations, and in this case here, so for example, if we have the s orbital for the oxygen, and we would have the s orbitals for the hydrogens. In this case here, they're all in phase, and it's a bonding orbital. And this right here would be our A1. Now, in the case of B2, remember we said that it's the py orbital, and the y is within the plane of the board, so we would draw this like this. And remember, we have a two different phases in the py orbital. And so in this case here, the bonding orbital in such case would be shaded on the right hand side and not shaded on the left hand side. And this right here would be your B2 bonding orbital, and this right here is the linear combination for this B2 orbital. Now, what if we look at px? So px was under B1, and we have 0 representations for B1. But if we actually try to draw a linear combination for such orbital, you'd realize that the px axis is actually coming out of the board and towards the back of the board. So if we draw this, it would look something like this. And if we add the the s orbitals for hydrogen, we would realize that there would be no net effective overlap, which means that if we actually look from the side here, we would be seeing that, so let's say the x-axis is coming this way. The s orbital for hydrogen would be right here in the middle. So the amount of positive overlap is equal to the amount of negative overlap, resulting in a net zero overlap, which makes sense because we do not have any representations in B2 for this water molecule. And also you'll realize later on in the course that you can use these to actually help you draw molecular orbital diagrams in which you can find which orbitals are involved in bonding, which orbitals are involved in non-bonding, such as the case of px orbital here, and you can come up with anti-bonding orbitals as well. Next we'll be looking at finding sigma and pi orbitals for compounds that involve multiple bonding. So in this case here we're looking at osmium tetroxide. Alright, in this case let's look at the tetrahedral molecule osmium tetroxide, in which we have osmium, and then we have 4 oxygens bound to it in a tetrahedral manner. So these oxygens, one's going behind the page, one's going in front of the page, while the other 2 are in the page. Now the point group of such compound is tetrahedral, TD, and if we were to look at the character table of tetrahedral, and this right here is a great website. It's Symmetry from Jacobs University, and I'll leave the link for this website in the description below if you want to check it out. So this right here is the character table for a TD point group, and you'll see those symmetry elements, and in this case here you'll see that the coefficients are actually greater than 1 in some cases. And so if we want to figure out the order of this group, it would be so 6 and 6 is 12, plus 3 is 15, plus 8 is 23, plus 1 is 24. So the order is 24. So we can refer to it as H. It's 24. And let's start by looking at the sigma bonding of such molecule. So we have the tetrahedral group, and we're looking at sigma bonding in this case. So we have E, we also have HC3, we have 3 C2s, S4, and lastly sigma D. Now if we keep the compound the same, we have 4 oxygens in this case here, so this would be 4 atoms that are in the same position. If we do a C3 rotation, so in this case here, remember from the previous tutorial, we're looking down something like an osmium oxygen bond, one of these oxygen osmium bonds. So if we look down one of these bonds, so behind this oxygen would be an osmium, and coming down would be those 3 other oxygens. And for simplification, I'm just showing the one bond in this case. So this right here would be your C3 rotation. Now if we do a C3 rotation, those 3 oxygens actually move. The only oxygen that stays in the same location is the one that is on the actual axes. And so in this case here, we only have 1 oxygen remaining in the same spot. Next is the C2 rotation. So if we're looking between those 2 oxygens, for example, you will see that if we have the osmium, we would have 2 oxygens pointing upwards and 2 other oxygens pointing downwards in this fashion. Therefore, if we actually do a C2 rotation, we would end up with all of these oxygens moving. So in this case here, we would have no oxygens remaining in the same spot. Now an S4 is a C4 rotation followed by a sigma H. And we'll do this stepwise. So we're looking at an S4 rotation. So first of all, we start with a C4, and then we follow that with a sigma H. So in this case here, we have a C4, so means we're rotating by 90 degrees. So if we have the osmium in the center here, the oxygen that is pointing downwards is going to rotate 90 degrees. So this oxygen will be here, and the one on the opposite end will also be pointing downwards, and the other 2 oxygens will be pointing upwards. So this right here is your C4 rotation. Following that C4 rotation, we do a sigma H. A sigma H is a perpendicular mirror plane to the principal axis. So we're looking at the mirror plane that is cutting through the molecule like this. So the oxygens that are pointing upwards will point below the plane, and the oxygens that are below the plane will point above the plane. So in this case here, we have osmium, and we return to the same arrangement of atoms that we started with, but do those oxygens move in this case? So if we label this 1, 2, 3, 4, for example, then oxygen 1 would have moved here, and in the final structure we have 1, 2, 3, 4. So it would not be the same positions of atoms in this case, and therefore S4 would lead to a 0. So you could have got it from the start, where we do a C4 rotation, all the oxygens actually move to start with, but we just walked through it to learn what the S4 symmetry operation is. Now in the case of a sigma D, this is a mirror plane that is cutting through the compound. In this case here, we would have 2 oxygens that are within the plane of that mirror plane. Therefore, those oxygens will not move, and only the oxygens that are to the right and left of that mirror plane that would actually move. So in this case here, we have 2 oxygens that remain in the same spot. Now we can actually go back to the character table and figure out the irreducible representation. So we would go through each one of these symmetry labels and figure out how many representations are in A1, A2, E, and T1 and T2. Now, A would represent one orbital. It's singly degenerate. E is doubly degenerate. It represents two orbitals. So you would see two orbitals together that are degenerate. And then lastly, T would represent triply degenerate orbitals. So three orbitals that you would have to consider at the same time. Now, with these operations, you can also use the other symmetry website, this right here, and you can actually it can actually help you a lot with determining the irreducible representation. So, for example, if we have a C3 rotation and we actually rotate the molecule, you'll see that those three atoms on the outside move, but not the one on the principal axes, like we have discussed before. Therefore, it was 1 for C3. If you go through the C2 rotation, which is cutting between two oxygens, in our case, all of the atoms move. And if we do an S4, so an S4 is where we do a C4, you can see it, a C4 rotation followed by a sigma H. And all of the bonded atoms move. Now lastly, if we look at one of these dihedral mirror planes, it would be cutting through two of the oxygens that we had, and the two oxygens that are to the right and left of the mirror plane would actually move, but not the ones in the actual plane. So this is a great tool to look at and learn things visually, and help you come up with reducible representations. Now we go back to the irreducible representation in this case. So if we work up the irreducible representation like we did the first time with the previous example, we would realize that in this case here we have the sigma bonding to be 1A1 plus 1T2. Now if you go back to the table, you'll see that the A1 is represented by the s orbital, and the T1 or T2, sorry, in this case would be the px, py, and pz orbitals. So we have four orbitals that are making up the sigma bonding in this complex, and they are s, px, py, and pz. Next, we'll be looking at the pi representation. So in this case here, we would create the same kind of table. So tetrahedral character table, and we have E, HC3, 3 C2s, and then we have the S4 and the sigma D. And now we are looking at the pi orbitals in this complex. It's the same idea as the sigma bonding, except now we are looking at two vectors on these atoms. So for example, in this case here, we would be looking at a vector that would be perpendicular in this case, and then a vector that is parallel, so parallel to the bond here. And now it's these vectors that we are looking at that we want to consider if they move or not. So first of all, if the oxygen by itself moves, we do not consider the vectors. They would be counted as 0. If the oxygen remains in the same position, then we would examine those vectors and see how they move. If the vector stays in the same, pointing in the same direction, it would be assigned a +1. And if it's pointing in the exact opposite direction, it would be assigned a -1. Now, one tool that you can use is the cosine function. So if we look at a vector, so for example, let's say the vector is pointing to the right in this case. If we have no rotation of the vector and the vector points in the same direction, the cosine of 0 would be +1. If the vector moves in the opposite direction, so we rotate by 180 degrees, which is a C2 rotation, so now the vector is pointing in the exact opposite direction, then this is assigned a -1. Now in the case of a C4 rotation, where we rotate by 90 degrees, now we are perpendicular to the starting vector, so we're not pointing in the positive or the negative direction, and this would be assigned a 0, and you can check by plugging in cosine of 90, and that would be 0. And in the case of C3 rotation, and this is a 120 degree rotation, the vector would be pointing in between the perpendicular and the plane or the direction of the vector, and the cosine of 120 would be -1/2. And this will come in handy when we look at these in particular. Okay, so if we keep everything the same, all the vectors will point in the same starting direction. Therefore, in this case here, we would have a total of 8 vectors that are remaining in the same position. Next, if we do a C3 rotation, and we can go back to this diagram here that we drew earlier, and we can actually take a look at the vectors. So for example, if we're looking at a vector that is parallel and a vector that is perpendicular, now it doesn't matter for the outside oxygens because these oxygens actually move with the C3 rotation. It's only this oxygen that remains in the same position, and we will have to consider. So if we redraw this after the C3 rotation, the vectors would actually, one of them point in this manner here, 120 degrees away, and the other one would point this way here, 120 degrees away from the starting position. Now, because it's going, each vector is going 120 degrees, so this vector would be assigned a -1/2, and this vector is assigned a -1/2 as well. So overall, we have a -1 for C3. Now remember, the other oxygens are zeros because they actually moved. In this case here, remember, each one of these was +1, +1, because all of these oxygen, all of these vectors remained the same. And so it was a total of 8 for E. For C3, we have a -1 because those two vectors moved by 120 degrees, so -1/2 each, overall -1. If we do a C2 rotation, you'll realize that all of the oxygens move in this case, and therefore this would be a 0. We don't have to consider the vectors. In the case of S4, it's the same idea. And lastly, if we do a sigma D, so let's consider this drawing right here. Now, two of those oxygens are actually going to be moving, and therefore we don't have to consider those. The ones, so this would be a 0, and this would be a 0 as well. Now if we have a parallel vector that is like pointing upwards, and then a perpendicular one, and then we have a parallel vector and a perpendicular one, if we do a sigma d in this case, we would end up with, so the oxygens here on the outside swap positions, and the ones that are pointing downwards that are within that plane would have the vectors that are parallel remain in the same position, and the ones that are perpendicular point in the opposite direction, because whatever is on the right of that plane will point to the left of the plane. Whatever is within the plane will remain within the plane. So in this case here we have a +1 and a -1. We have a +1 and a -1. Overall it comes up to be 0. Now that we have the reducible representation, in this case for pi bonding, we can come up with the irreducible representation by looking at the table here and considering each of those symmetry labels like we did in the previous case. So let's walk through the first example, A1. So in this case here for A1, we would have, so 8 for the reducible representation number times the coefficient here is 1, and in the table the character is 1, so it's +1 for all of them in the A1. And then we have -1 times the coefficient here is 8 times +1, that is the character in the table, and the following 3 are all going to be zeros. Alright, so if you remember, the order we said is 24, and so in this case here it's 8 minus 8 over 24, so there are 0 representations for A1. Next is going to be A2, and there are 0 representations in A2. Let's take a look at E. So in this example we have E. So 8 times 1 for coefficient times +2, and then we have -1 times 8 times -1, and then zeros all over 24. So in this case here we have 8 times 2, so that's 16 in this case, and then we have -8, so we have +8, so together it's 24 over 24, and we have 1 representation for E. So if you solve through them, you'll realize that the irreducible representation in this case, 1E plus 1T1 plus 1T2. So from E, we see that the orbital involved is the dx square minus y square and the dz square. So we have dx square minus y square and the dz square. So those are 2 orbitals for pi bonding. For T1, however, we do not have any orbitals with appropriate symmetry, d orbitals, to actually form pi bonding. In the case of T2, we have the option of px, py, pz, which we used for sigma bonding. And so for the pi bonding, we have dxy, dxz, and dyz. So for T2, we have dxz, dyz, and dxy as well. So you'll realize that we actually have 5 bonding orbitals in for pi bonding in osmium tetroxide. So if you are to actually figure out the bond order at first thought by looking at the Lewis structure, one might think that the bond order of the osmium oxide would be 2 because it's just a double bond. But if you consider the orbitals, you realize that you actually have 4 orbitals from the sigma bonding, and then you have 5 orbitals from the pi bonding over 4 oxygens, 4 times the oxygens, and therefore the bond order in this case should be 9/4, which is slightly more than bond order of 2. And so in this case here, we actually went through character tables, figuring out how to use those to actually come up with the sigma bonding orbitals and the pi bonding orbitals. In the next tutorial, we'll be also looking at character tables, but we will be extracting vibrational modes, and we'll be seeing how we can actually use those vibrations to learn more information about a given compound.